Now that I've introduced myself, I'd like to introduce you to our department at MIT, the Department of Aeronautics and Astronautics. In 2014, we celebrated the 100th anniversary of the first class in aeronautical engineering that was ever taught at MIT, and the 75th anniversary of the establishment of our department. MIT loves numbers, and our department is referred to as Course 16, which is why the introductory course that I teach is called 1600, and why this online course is called 1600X. So let's take a look at the history of MIT's Department of Aeronautics and Astronautics.
Wilbur and Orville Wright, the first men in the history of the world to pilot a heavier-than aircraft in sustained flight under power and control.
The Wright brothers were great pioneers in the way they approached the problem of flight.
The speed about 40 miles an hour, altitude, as you see, about 75 to 100 feet.
There are a lot of different ideas about what an airplane should look like and what the wings should look like, but there's not all that much data out there. They combined empirical studies in a wind tunnel with the actual desire to build an airplane and learn how to fly it. MIT brings that combination to the next level. To really build the tools, build the instruments, take the data, compare it to the physical principles, and understand what you're doing.
What we have done is largely focused on the software challenges. What are the algorithms that allow different kinds of sensor information to be brought together and fused into a consistent estimate of where the vehicle is and what's around it? How do you plan trajectories through the environment that are safe, that allow the vehicle to move quickly and without collision? How do you incorporate information about what's in the world? How do you incorporate sensor information that tells you what's changing? And how should the vehicle construct new plans in order to react to that new information? Small air vehicles are just going to become part of our everyday existence. They're going to be a new source of information about the world, and they're going to be a new way to move things around. And we're just going to take it for granted 100 years from now.
Aeronautical engineering is a funny kind of engineering because it's really a kind of systems discipline from the beginning.
There is the systems problem of how do you integrate these vehicles safely? How do you integrate these vehicles reliably? How do they do all the things they need to do without getting in each other's way? I mean, that's a huge research problem that's going to take many years to solve. And I think there's an opportunity for us as a department to really be part of the solution.
Airplanes are the glue that knit the global system together, but the focus is on making them more efficient, on making the system more efficient, making it more environmentally friendly.
The idea was design an airplane that could save 70% fuel. If you think about a fuselage, it's one single bubble, and this one is two bubbles, so the fuselage is wider. It lifts more. Even the Wright brothers had a wind tunnel because you want to know what's happening. Is this airplane actually flying? Is it going to lift off? Is it not? And then you want to be able to change things in a controlled environment. All right, tunnel on. So I'm going to go first gear and then second gear. The tunnel is blowing 100 miles per hour on the model. We're actually having a big computational effort, and they're actually simulating exactly the conditions we're running in the tunnel. Did Neil give you the okay? So you can validate things for the computations, and then the computations can do much more than you could do because your tunnel is limited in speed or whatnot, but their computations isn't. So I think experiments, wind tunnels, computations, you can make an airplane out of that.
Start at 0, idle, hold for 2 minutes, get the okay.
Yeah.
Increase power to 14,500.
MIT's model for a research university has always been that the best way to educate students is get them involved in the research.
Okay, tunnel speed is off. Shutting down the tunnel. I'll tell you, I have a bet with a friend that this thing is going to fly within the next 20 years.
Each person in this department has some kind of drive within them, some kind of problem that they want to solve.
The Spheres project is one of the really cool projects in the Space Systems Lab. They actually have satellites inside the ISS that they can control and send different algorithms to improve the way that we design satellites and operate with the astronauts.
Like Greg and Katie, I studied science, math, and engineering at MIT, and it's taken me on a wonderful path of discovery and adventure.
We have two different motors, and the way the pitch is controlled is by a servo that can tilt the entire kind of axis.
The main strengths of the department are its people. It's faculty, it's students, it's industrial partners, it's alumni. It's really the community we have been fortunate to be able to create.
You're going to go a lot faster if you go straight, as opposed to if you're zigzagging. So control is really what makes or breaks this competition.
The best part of each and every day that I have here is meeting with my students, working through research problems. We are incredibly fortunate at MIT to have the best students in the world.
It's the people around you that definitely keep you going, and that's one of the main things I love about this department.
It's really very humbling to see what people before us have done.
MIT is best known for the scientists and engineers who have studied there.
It started with a vision, but then we've just been tremendously fortunate to attract the people we've been able to attract, whether it's Hans Sacker, Doolittle, Draper, tremendous individuals who've made major advances.
This kind of basic research into control and estimation, sensing, et cetera, has been a part of our department's history for many, many years. The instrumentation lab at Draper, the Apollo missions were all things that came out of this department, and it's great to be continuing that tradition.
We've been fortunate to graduate a large number of astronauts, whether it is Apollo or a space shuttle. It's something that happens. We do not have a deliberate attempt to really attract astronauts per se. I think it's a byproduct of the way we do research and the way we do our work.
We just want to say hi to everybody.
Still to this day, if young people say, what do I have to do to become an astronaut? Go get a PhD at MIT is a pretty common answer they'll hear.
This length is actually 5 millimeters.
People in this department, at MIT, in Aerospace in particular, they're very excited about what they do.
Okay.
Who gets to go to the moon? Who gets to launch a rocket, right? Who gets to design the next airplane? And I think that's what you have to do in life. You have to do what you like. People do it because it was their dream.
So we're trying to enable astronaut performance on the moon or Mars, get back to the planets, and it's kind of extreme. We're really going to be going up very steep terrain. We're going to be going down, looking at craters. How can we design spacesuits and life support systems to enable that exploration? The current traditional spacesuits are big gas pressurized balloons. They're very immobile. They're very heavy. We kind of flip that and say, no, we want a 20 kilo, an order of magnitude reduction in mass for sure, as well as maximizing the mobility. If I'm going to design a suit that applies pressure directly over your skin, essentially I'd like it to be a second skin. That's the real research question. How can I make a second skin? We need to apply a third of an atmosphere. So our design goal is 30 kilopascals. That's the same pressurization of the gas pressurized suit. So we're trying to match the current system, but now get rid of the gas, get rid of the balloon, put the pressure directly on the skin, and we think this patterning is really important. I like to describe it lots of times as a smart zipper. So you don this, you put it on, it's comfortable but maybe a little bit loose, and if you apply then the active materials and it shrinks it up to get to our desired pressure state. They generate actually a lot of force when they're activated. This is just stainless steel wire, but now imagine this was the shape memory alloys that we just played around with. So if I open this up, gonna give you a couple extra centimeters here to don, to jump into, right? Rather than me doing it mechanically, the shape memory alloy, when it's activated under the voltage or the heat, it cinches it up.
Space is not quite the technological frontier it was in the 50s, where it was a bit of a Wild West. The challenges that we're left with in space are really very hard challenges, and they may not be solved by new inventions. They may be solved by kind of some end runs around some of the difficult problems.
I think in 60 years, we'll have been on Mars, becoming a multi-planet species, getting out of the cradle of Earth permanently.
Soon we may overpopulate the Earth. We may actually need to look outward.
We're going to be able to point up at skies in our local neighborhood and say, There are water worlds there, there, and there. Is there intelligent life on them? How do we communicate with them? And how are we going to get there?
We're going to have a lot of intelligent systems in the future and more automation and more intelligent automation.
Archaeology is like, discovering more about our past and understanding of where we've been. And I kind of see Aeroastro as like understanding of where we can go.